Hi, this is my video number 5 for differential equation. Okay, so in this video I'll talk on singular eigenvalue problem. Singular eigenvalue problem. Okay. Now, till now we have studied the case, the differential equation of the form. Yeah, we have studied the integral equation of the form. We have px y prime y plus qx y plus lambda rx y equal to 0 on interval AB, where in this case we assume that P prime, Q and R are continuous. This is continuous on AB, and Px is different than 0, yeah, for all x in AB. Now, if you consider, if you let P prime, Q and R continuous on AB, and Px different than 0 for x in AB, but at the endpoints, we have this is, let's say, our interval here, A and B. Yeah, so this is the endpoint. This is the endpoint. But I think this should be like that, open interval. Okay. And at x at endpoint x equal to A, x equal to B. So we have the following properties. The following properties occur. That P vanish, which means P at A is equal to P P at A is 0, or P at B is 0, or both. Yeah, both 0. Both means P equal to 0, PA equal to 0, PB equal to 0. Or we can also have one or more function P, Q, R becomes infinite. So, for example, we may have R in terms of let's say x over A or x over B, x minus B, or so on. And this is just an example. Example. Or maybe Q is of that form, or P is that form, or that's we call continuous, because as x come close to A, so you can see the whole function here blow up. So this kind of problem, we call it as a singular eigenvalue problem. This kind of problem is called a singular eigenvalue problem. Singular eigenvalue problem. Okay, and for self-adjoint problem, self-adjoint problem to be non-singular, for the self-adjoint problem to be non-singular, or we can also say regular, on AB, the interval. So we must have this relationship must be satisfied. That's AB VLU minus U LV. This is equal to 0. So if you do this using integration by parts, where your L is given here, your L is given here, so you can see your L is px bx y prime qx plus lambda rx. So that's your L. So you apply with respect to u and in respect to function y, where u and v is twice differentiable function. So this, if you do this using separate integration by parts, you may have you may end up with this. This is just easy to do it. So you just follow the integration by parts. So you have u prime b vb minus ub v prime b, okay, minus PA U prime A VA minus UB V prime UA V prime A, and this must be equal to 0. So you have self-adjoint equation for a non-singular that we have dealt earlier. Okay, so this must be true, and the function in this case u v is so if you differentiate that, it's still continuous on AB, and also satisfy the boundary condition, satisfy the given boundary condition. So in this case, it's ensure the orthogonality. If you have this kind of self-adjoint problem, then UV are orthogonal. Now how do we relate this with a non-singular case? Now so let's say our function singular at one of the points. Consider the problem which is singular at x equal to a. So what we do here, so if you have, this is our interval from a to b, okay, if at this point, let's say p equal to 0, vanish, or p undefined, so what do? We remove a little bit there, so with, let's say, distant delta. So what happened, instead of we integrate from a to b, Now we integrate from a plus delta, which is a little bit there, we remove that point, and b, and then we make it the limit delta goes to 0. Everything inside is just the same. Okay, that's what we're going to do. Now if we do this, then from the self-adjoint condition that we have, instead of a, we have a plus delta to b, v lu minus u lv dx. Okay, if you do this, you're going to have pb u prime b vb minus ub v prime b minus, here we have p because we evaluate at delta a plus delta here, so p a plus delta u prime a plus delta v a plus delta minus u a plus delta v prime a plus delta. Okay, so in this case you have u and v are continuous, on interval, so I can say uv is c1, which is continuous derivative ab. Okay, so if we impose the condition, on v, u and v, to ensure that on u and v, to ensure that the limit as x approaches a from positive. So if you look at our interval here, we approach x approaches a from positive, so we have px u prime x vx minus ux v prime x, that's 0. And also we have condition fb u prime b vb minus ub v prime b is 0. So why do we do this? Because if x approaches a from positive, so look at this, if x approaches a from positive, so what does it mean? So it means that we take delta small enough, or I can say we take the limit delta tend to 0. So what happened if delta tend to 0? If you look at this, delta tend to 0, so this a plus delta tend to 0, so it's come very close to the point A. So if we impose this condition, okay, x approaches a from positive, that's 0, and at the other point p, at the point b, so this is also 0, then what happened to that property that we have? Then we have this integral ab v lu minus u lv, this is 0, which is true again. Then we have this relation is again true. Okay, so what does it mean? So it means that even though we have a singular problem at point A, since we remove exactly at point A, add a little bit small amount delta there and make it delta close enough to 0, then we can make this singular problem as self-adjoint still. Okay, so for example, so the condition y prime x are finite as x goes to a from positive, and the boundary condition gamma yb plus delta y prime b, this is 0. So this boundary condition will ensure the equality. So let me call this equality. Let me call this as a star. Okay. So this ensure the equality star is satisfied or is true. Okay, this is for the case where the singular point is at point A. So what if the singular point at point B? Yeah. For the case of singular at x equal to b, so now we consider the interval. We have a, b, this is delta, so which means that point is beta minus delta, and b minus delta. So we consider that interval. So for the case of singular at point x equal to b, so we consider the interval a, b minus delta, and again we allow delta goes to 0, so make it delta small enough so that we have this point very close to point B that we are looking for. Now if PB is 0, then the boundary condition, we have gamma ya plus beta y prime a, that gives you 0. Okay, I think this is alpha, should be alpha, and we have yx and y prime x are finite as x approaches b from negative. So this will ensure that this condition AB, the self-adjoint condition LV, they're equal to 0. Yeah, for function u and v satisfies the given boundary condition. Okay, so now we have considered singular at point A, and we also have considered singular at point B. For both of the cases, we can show that the problem still self-adjoint. So what if we have singular at both points? So if you have A here, if you have B here, again we can take out small amount delta. We can take out small amount delta. Then instead of we integrate from A to B, now we integrate from A plus delta to B minus delta. And again, inside here ULV minus VLU, that we need to show this equal to 0. So by following the same step as above, you can show that this equal to 0. Okay. So what we have in this case, so at this point, if let's say P A equal to 0, PB equal to 0, which is in this case, yeah, both are singular at endpoints. Singular point at both singular points, P A and B. So the boundary condition. So we have yx, y prime x are finite when x approaches A from positive, and yx, y prime x also finite when x approaches B from negative. And therefore we can ensure that this condition is still satisfied. Okay, so which means the singular eigenvalue can also be made as a self-adjoint problem. Okay, for example, where in this example I won't give a full solution. Instead, I want you to try by yourself. You can refer to any differential equation book. Yeah, example, you may consider a Bessel function, Bessel equation. So we have dx as x y prime minus v squared over x y plus lambda x y, that equal to 0. And we have y x y prime x remain bounded as x goes to 0 from positive and y1 is 0. You can show this, show that this equation, let's call this as a star, that star is self-adjoint. And also you can try to find the solution and solve it. Okay, so the solution is given as we have yx is equal to c1 j mu lambda, this is lambda x plus c2 y mu lambda x, yeah, where this is Bessel function of the first kind, this is Bessel function of the second kind. Yeah, Bessel function of the first kind, this is Bessel function of the second kind. Another example that we may consider the Legendre equation, Legendre equation, which is given as d dx 1 minus x squared y prime plus lambda y that equal to 0, yx y prime x bounded as x goes to plus minus 1, and you show that this equation, let's call double star, show that double star is self-adjoint, and solve it. The solution, this is the solution. So the solution is given as yx is equal to 1 plus summation k from 1 to infinity minus 1 k n plus 1 k over k factorial 1k 1 minus x over 2 to the power k, where this notation means minus n plus 1 minus n plus 2 and so on up to minus n plus k minus 1. Okay, so up to now I have discussed you what is the singular eigenvalue problem, what make it singular, what make the eigenvalue singular. We have a certain condition that P depend on P, Q and